So now we're going to take a look at electrophilic aromatic substitution reactions of substituted benzenes. So let's say we have a benzene with some type of substituent, let's call it G, and we react it with an electrophile. We see that we can get the electrophile to add in the 2 position relative to G, or in the 3 position relative to G, or lastly in the 4 position relative to G. So just like we saw in the previous section with heterobenzenes, when you have a substituent on, then you have this regio chemistry that's taking place. So when you get substitution on the 2 position, we call this ortho substitution. When you get it in the 3 position, we call this meta substitution, and in the 4 position, we call it para substitution, right? Because we're creating ortho, meta, and para derivatives. So how do the substituents that are already on the ring influence the substitution? Well, we're going to see that they, number one, influence the regioselective distribution of products. So some groups direct the electrophile to the ortho and para positions, and we call these OP directors. And some substituents direct to the meta position, and we call these meta directors, M directors. So, so we see that there is some regioselectivity, and we're going to talk about why that is in just a little bit. But there's also an effect on the rate of the reaction. And in general, most OP directors react faster than benzene. If we use benzene as kind of our staple, and we look at the rate of reactions of derivatized benzenes, we see that OP-directed substituents actually react faster than benzene, and all meta-directors react slower than benzene. Okay, so let's take a look at a table of substituents and see how how these how different types of substituents kind of play out. And we see that so we're going to list them: the group, the position, whether they're ortho-para directing or meta-directing, and then the relative rate. And this is going to be relative to hydrogen. When you have amines that are on the benzene ring, amines are OP directors, and their rate of reaction is very fast relative to benzene. Likewise, alcohols are also OP directors and very fast. Alkoxides as substituents are OP directors and very fast. When you have an alkyl group on the ring, we know alkyl groups donate electron density. We'll talk about that in just a bit. They're OP directors, and they're fast. They're not quite as fast as the first 3 types of groups, but they are fast relative to benzene. Likewise, you can have an amide coming off of the benzene ring, where the nitrogen is attached to that benzene ring, but the nitrogen has a carbonyl group attached to it. These are OP directors. They're fast, but not as fast as amines are. And of course, then we have hydrogen, which has no direction to it, so it has a relative rate of 1. And halogens are also OP directors, but they're slower than that of the reactivity of just benzene itself. I can have sulfonic acid group on the benzene ring. It is a meta-director, and it is slower than benzene. Any carbonyl that's attached to the benzene ring is a meta-director, and it's slower than benzene. An NO2 group is a meta-director and is slower than benzene. A nitrile, right, where the carbon is connected to the benzene ring. Also a meta group, meta director, and is slower than benzene. And lastly, when we have ammonium salts, where the nitrogen has a positive charge on it, it's a meta director, and the relative rate of the reaction is slower than that of benzene. So let's take a look at the activating groups and why um, they activate the ring and why they have the regiochemistry that they have. And I'm going to use anisole as an example. So I have this OCH3 group on the ring, and I can look at a chlorination of anisole. Now, notice, so ORs, very reactive, right? So, and their relative reactivity is very fast. Notice in this reaction, when I halogenate, I don't need to use any type of catalyst, because the substituent activates the ring toward electrophilic aromatic substitution. And as a matter of fact, we're going to see that it donates electron density, enhancing the nucleophilicity of the ring itself. So when I chlorinate, I get if I look at the distribution of products, right, I can get para-chloroanisole, ortho-chloroanisole, or meta-chloroanisole. And when I look at the product distributions of these, I see that para-chloroanisole yield is 65%. Ortho-para-anisole yield is 35%. And if you can quickly do the math, you see that meta-chloroanisole doesn't even get made whatsoever. So here we have that regioselectivity, where the OCH3 group, the group already on the ring, directs the chlorine to either the para position or the ortho position, not the meta position. And when we think about why this is, just like in the previous section where we looked at the stability of the intermediates, we can look at the stability of the intermediates in electrophilic substitution of anisole itself. And so we're going to start off talking about the para substitution, right, because it has the highest yield. So what's going to happen in the mechanism of substitution with chlorine? We know that a pair of electrons, right, are going to attack chlorine and displace a chloride ion. So the pair of electrons I'm choosing, you have to, think about the positions. I have to choose a pair of electrons that reside between C3 and C4 in order to put chlorine on C4. And so I get this particular intermediate, right? I've added the chlorine. Notice I could have added the chlorine on the meta position or the para position. If it's on the para position, because that's what we're focusing on, then the carbocation is on the meta position relative to the OCH3 group, right? And of course I have, I can draw resonance structures of this, and we've seen many times how the ring distributes cyclohexadienyl carbocation. And so here is one of my resonance structures. Notice the positive charge is on the carbon with the substituent OCH3 on it. And then of course I can draw that third resonance structure, typical resonance structure, where the positive charge now is again meta to that OCH3 group. Now, if I look closely, I see that I can draw another resonance structure. The oxygen has two pairs of electrons on it, and so through the pi system, I can donate a pair of electrons from oxygen onto that carbocation, and I get another resonance structure, where the positive charge is now taken off of the ring, placed onto the oxygen. Now, if I look at these four, now I have four resonance structures, and I look at the four resonance structures and I decide which resonance structure is the most favorable, you might be inclined to say that um, the kind of that middle one there where the positive charge is on a tertiary carbon. But in fact, the one at the bottom is the most stable. And the reason for this is even though the oxygen has the positive charge and it's the most electronegative element, if you notice all of the atoms have an octet of electrons around it. And so when we look at stability of Lewis structures, we know that if all atoms can satisfy the octet rule, then that produces the most stable contributing resonance structure. So that where the positive charge is on the oxygen is the most stable contributing resonance structure. All right, so let's look at ortho substitution because we see that there is some ortho substituted product of this reaction. So in this mechanism, we're going to use the pi electrons that are on the right-hand side of the ring. Again, we're displacing a chloride ion, and we place the chlorine, the electrophile, onto the ortho position, and in the meta position you create that carbocation. And again, we can draw resonance structures of this where now I'm taking a pair of electrons, donating it to the carbocation, and I get a new allylic carbocation here, and then of course I can do this one more time and I get the allylic carbocation here. Again, notice in ortho substitution, that positive charge goes onto the carbon with the OCH3, the group that's already on there. And so again, it has, I can take a pair of electrons and donate it into that carbocation, and I get that new resonance structure, which again is the most stable contributing resonance structure. And so you see that when we get ortho substitution, there are similarities between it and para substitution, in which the positive charge always goes onto the carbon that has the substituent on it. That substituent, if it has a lone pair of electrons, can donate those lone pair of electrons in through resonance, creating that fourth resonance structure. And so this is very important to recognize that all of those highly activating substituents have lone pair of electrons. Amines have lone pair of electrons. OH has a lone pair of electrons. And then, of course, OR, like we have here in OCH3, has lone pair of electrons that can contribute to the fourth resonance structure. So when we look at meta substitution, again, notice it's going to be very similar initially to ortho substitution. I'm going to use the same pi electrons to donate to my electrophile chlorine, generating a chloride anion. And yet this time, the intermediate here, excuse me, the chlorine is placed on the meta position. The carbocation now goes ortho to the OCH3 group. And when I draw resonance structures, I see that when I move my electrons down to that carbocation, I generate the carbocation basically moves to the left, and then of course I have another resonance structure where the carbocation can be at the bottom. And that is it, right? I only have those three resonance structures. And so I see that I can only generate three resonance structures, and that the group, the OCH3 group, cannot participate in resonance stabilization. So with para and ortho substitution, the lone pair of electrons on oxygen can donate to create a fourth resonance structure, stabilizing the intermediate. With meta substitution, that stabilization cannot happen. And so the activation energy for meta substitution is going to be higher than the activation energy for ortho and para. Now one may ask, well, why do you get more para versus ortho? And generally speaking, it simply has to do with steric effects. Even though there are, in essence, two ortho positions, steric effects tend to put the second substituent farther away from the first substituent. All right, so if we think about deactivating groups, you know, why is there a difference between activating groups and deactivating groups? And I'm going to demonstrate this with benzaldehyde, right? So we saw in the deactivating list, anything that has a carbonyl attached to the ring is deactivating. So here we have an aldehyde, and that carbonyl of the aldehyde deactivates the ring. When I try to nitrate it, I get meta-nitrobenzaldehyde. And the yield's pretty high, right? 84%. And of course, the remaining 16% is going to be ortho and para substitution, but we see that the major product is meta substitution. Now, when we think about why this is the mechanism going to be different? Obviously, it's not. The mechanism is always the same, right? So this is something that we have to think about. The mechanism doesn't change. The effect of the substituent must be changing the stability of the intermediate. So when I look at meta substitution, I know in a nitration the nitronium ion is the electrophile, and so if I'm adding that nitronium ion to the meta position, I'm going to take those pair of electrons on the right hand side of the benzene ring and attack the nitrogen, displacing a nitrogen-oxygen double bond, and I generate my cyclohexadienyl carbocation, where the carbocation is ortho to the aldehyde, right? And as we just saw previously, we can draw resonance structures, placing the positive charge on the left-hand side of the aldehyde, and then another resonance structure placing the carbocation para to the aldehyde. So para substitution, again, is going to be the same thing. So now I'm going to take the pair of electrons on the ring that's bottom and donate it to the nitronium ion. I generate the carbocation where it is now meta to the aldehyde, and I can draw my resonance structures, right, placing the carbocation on the carbon connected to the aldehyde, and then on the carbon on the right-hand side of the aldehyde. And so again we see three resonance structures. So what makes this different between meta substitution? Well, again, we're going to focus on that middle resonance structure, the carbocation that is attached to the aldehyde, right? And if we think about the substituent effect, right, with OCH3, the oxygen had a lone pair of electrons, and it could donate those lone pair of electrons into the ring and create a fourth resonance structure. When I have the carbonyl, I see that with carbonyls, they're polar. The carbon has a partial positive charge, the oxygen has a partial negative charge because oxygen is more electronegative than carbon, and it withdraws electron density away from that carbon. And so if I look at this particular intermediate, this resonance form of the intermediate, I see that now I have in essence two positive charges right next to each other. The carbocation is connected to a partially positive carbon, and because of this we have a destabilization effect, right? Two adjacent positive charges next to one another. And so what happens is the activation energy of para substitution and likewise ortho substitution actually increases, right? Because the energy barrier to form that carbocation connected to an atom that has a positive charge on it, or a partial positive charge, is going to be greater than if we simply avoid that group. And therefore, meta-substitution occurs because the activation energy for meta-substitution to form the intermediate for meta-substitution is less. Now, so far, we've talked mainly about resonance effects, right? But of course, we know that there are two main effects. One of them is resonance, but the other is an inductive effect. And this is, of course, through a sigma bond, right? So when I take a look at, and I'm going to go back to anisole and thinking about the electronic effect of anisole, right? So we see that there's a resonance effect. That resonance effect essentially stabilizes the intermediate, and it also enhances the rate of the reaction, right? Well, inductively, if we think about carbon-oxygen bond, that sigma bond, oxygen is going to withdraw electron density away from that carbon and away from the ring, right, through that sigma bond. And so this decreases nucleophilicity. And when we're talking about, and I want to really emphasize this, when we're talking about electrophilic aromatic substitution reactions, the aromatic ring is the nucleophile, right? And it's attacking an electrophile. So we have to think about the nucleophilicity of that ring, right? Inductively, oxygen withdraws electron density from the ring, and therefore it's going to hold its electrons tighter, typically, right? And so nucleophilicity should be suppressed. However, through the resonance of the two of the pair of electrons on oxygen, we see that oxygen can actually add electron density through the pi system. And it's that pi system that is the nucleophile, right? The HOMO of the pi electrons is what is really attacking the electrophile. So because oxygen can add electrons to it, this actually increases nucleophilicity. And so we see that there are these two contradictory situations. Inductively, it's going to withdraw electron density. Through resonance, it's going to donate electron density. And in, of course, this particular case, we see that resonance certainly outweighs an inductive effect. And because of that, the rate of the reaction increases, and also we see a stabilization of the intermediate, and so and in effect that guides the regioselectivity of the reaction. Now, if I take a look at halogens are a little bit different. We saw on the table that halogens are OP directors, but the rate of the reaction is actually slower than that of benzene. So if I am looking at a halogen and I add an electrophile to it, and let's say it's on the pair position. Well, again, inductively, the halogen withdraws electron density, and it does it very, very well. And so we get this, again, partial positive charge on the carbon, partial negative charge on the halogen. And that translates into when, as the electrophile is adding, we have a partial positive charge. As it adds, we're, creating a partial positive charge onto the ring. And so again, this positive interaction is going to raise the activation energy, and it slows the reaction down. So this strongly withdrawing power of halogens slows the rate of the addition of the electrophile. In essence, it's suppressing its nucleophilicity. Now, once the electrophile has added, however, you see that I create this cyclohexadienyl carbocation, and of course I can draw resonance structures of it, right, putting the positive charge on that carbon with the halogen, and then of course that third resonance structure where I migrate it over to the right. But we also know that halogens have a pair of electrons. They actually have three pair of electrons around them, right? And so I can take one of those pair of electrons and donate it into that carbocation, generating a fourth resonance structure, right? That looks like this, where the chlorine has a positive charge on it. And so we have a resonance stabilization of this particular intermediate, whereas we don't have that in the meta position. And this is why halogens direct in the ortho and pair position, because they still have a lone pair of electrons that they can use to donate into the ring. So when I take chlorobenzene and I treat it with nitric acid and sulfuric acid, so I'm nitrating the ring, and I get para-nitrochlorobenzene and ortho-nitrochlorobenzene in a 70-to-30 ratio, and I get 0% of the meta substitution.